Go ahead.
Okay. Let me get out my...
I have a lot of geometry students, and a number of them have sent me their review material for the final. Now, they don't necessarily go to the same school you do or in the same class, so...
You want to use a rock canyon?
No, they go to Chatfield, most of them.
Oh, I know Chatfield.
Yeah. So it's better if you give me your review materials that your teacher handed out. Go ahead and try to verbalize them, and we'll do as much.
This one's just a trapezoid.
Okay.
It has 9 on the top, 11 on the bottom, and there's a line in the middle that goes through the middle of the, not up and down, but left and right, that has 3x plus 1.
Like that?
It's just like...
Oh, it's the midpoint line.
Yeah, like that.
That 3x plus 1 is the average base. In other words, we're looking at a trapezoid whose top base is 9, whose bottom base is 11, and that's the midpoint. So the length of the mid base you would expect to be what?
Right in the middle.
What is that number?
You would be 10.
Right. In other words, you're going to add 9 plus 11 and divide by 2. So we know that 3x plus 1 must equal 10. Now when you solve that, what do you get?
You get 3, right?
Yeah.
Okay, that makes way more sense.
Yeah.
I did not know what I was doing with that. I don't know why.
And in fact, there's probably a mark there and a mark there, which tells you that that's the midpoint.
There isn't, though.
What's that?
There's not a mark there.
Okay. Well, we have to, in other words, we couldn't really answer the problem unless they tell us something about the location of that line. It's got to be a midpoint line, or else we don't know how to do the problem.
Yeah, that's what I think too.
Okay. What else you got?
Okay. Let's see here.
So this phone number that you called me from, is that your cell phone number?
Yeah, this is my cell phone.
I'll make sure I put it into my contacts list when we're done here.
Okay, and I'm just trying to find the right problem though.
Okay.
Could we do class? It's just like they give you 3 numbers, and you classify it with based on like acute, obtuse, or right, and the numbers are 6, 12, and 9.
They want to know whether this is obtuse, acute, or right. Okay, well, if it's a right triangle, this would have to be true, right?
Yeah.
In other words, the hypotenuse would have to be the 12.
But it's not a right triangle.
No, because that doesn't satisfy the Pythagorean theorem. In other words, 6 squared plus 9 squared is not equal to 12 squared. So it's not a right triangle. And the fact is that 6 squared is 36 plus 81 comes up to 117. Well, 12 squared would be 144, right?
Yeah.
So it must be an acute triangle. Hold on. No, let me think for a minute. In other words, if I were to draw a right triangle, this would be the square root of 117, which is a number smaller than 12. So if I were to draw a right triangle, it would have to look like this. It would be 6, 9, and something less than 12, right?
Right.
So since this is 12, this has to be an obtuse angle. It has to be greater than 90.
Yeah, because so the Pythagorean theorem is applied to this no matter what, pretty much.
Yeah, pretty much. And then you just decide whether the hypotenuse of a Pythagorean theorem given these two sides is equal, less, or greater than that hypotenuse. You have another one with 3 different numbers?
Yeah, it's 7, 11, and 9.
Okay, so we're going to assume that it's right and then see how it varies from being a right. Okay, so how would I do this?
You multiply 7 times 7 plus 9 times 9, and then make it equal to 11 times 11.
Well, not to make it equal, because it doesn't equal that.
Well, put it in, make it
right, but 11 squared is 121. So if this was a right triangle, this would have to be 121.
Yeah.
Which means, let's see, there's got to be an easier way to do this. Let's see. Which means it has to be an acute triangle. In other words, if this was a right triangle, this would be the square root of 130, which is a number bigger than 11. Okay. So to make the hypotenuse less than this number, we have to shorten it to get it to be 11, and that makes that angle acute. You understand the logic of it?
Yeah, because, well, if the two numbers added up are bigger, then it's obtuse.
Yeah, well, right, exactly. That's exactly what you do. If it's bigger than, well, no, hold on. If it's bigger than that squared, it's going to be acute. In other words, here, let me draw what the right triangle would look like. This side would be 7, that side would be 9, and this side would be 11 and change, right? Square root of 130. Somewhere between 11 and 12. So it's 11 plus. Well, the fact that they're telling us that this side is 11, the only way I can make that side 11 is by shortening that hypotenuse. And the only way I can shorten that hypotenuse is to change this from a 90-degree angle to something smaller than a 90-degree angle. In other words, if I change it to something like this, where it's 7, 9, now that distance is no longer going to be 11 plus. It's going to be shorter than that. And in fact, it would be 11 because that angle is acute. You can do it by memorizing the formulas, but it should come out the same unless I'm looking at it improperly. But I don't think I am. It sounds like the formulas are telling you the opposite, though. First of all, look at this picture here. If they gave you 7, 9, square root of 130. Let's replace that 11 with square root of 130. That is a right triangle, correct?
Yeah.
Okay. Well, if that is a right triangle, but instead of being the square root of 130, it's the square root of 121, which is what 11 is, then this is not going to be a right triangle. It's going to be an acute angle here. Because the only way I can shorten up this length right here is by making that acute angle instead of a 90-degree angle. If I wanted to lengthen this segment, I'd have to make this angle obtuse.
Okay.
The first problem we did, we had to make this side longer. So it needed to be obtuse. Notice, I mean, this might be something that's not obvious to you, but it's worth noting. Let's take the 3, 4, 5 triangle. We know that's a right triangle, right?
Yes.
Well, what if I told you that we had a 3, 4, 6? Do you see that for me to turn this 5 into a 6, I've got to make this angle bigger? In other words, I need it to look more like this. That's still 3, that's still 4, but now that's longer than 5. That's 6. In other words, if this is bigger than the right triangle would be, it's going to be obtuse. If it's smaller, it's going to be acute. If it's exact, it's going to be a right triangle.
Okay. So if it's...
Yeah, it's hard to put into an equation. It almost has to be something you can see. Actually, you probably can put it into an equation. Yeah, you can. If you square the two smaller numbers.
But in the short run, if the square root, if the hypotenuse is bigger than the other two, then it's obtuse, right?
It's not whether the hypotenuse is bigger than the other two. It's whether the square of the hypotenuse is bigger than the square of the other two. Then it's obtuse. In other words, in this case over here, we have the square of the hypotenuse is 36. The sum of the squares of the other two is 25. Since 36 is greater than 25, it's obtuse. Whereas if I made this number 4.5, make it 4.1, now the square of it is less than 25. And if it's less than the sum of the squares of the other two sides, then it's acute. And that's the simple way to do it. You don't have to do it graphically that way.
Okay,
so just take your longest side, square all three numbers, take the biggest number and determine whether it's less than, equal to, or greater the sum of the two smaller numbers squared.
Okay, can we move on?
Yeah, for sure. Always.
Trying to find a problem that for sure you're going to not do correct.
Let's see, that last problem was nobody from Chatfield has that problem.
Yeah.
That's a Rock Canyon or Highlands Ranch area special.
We do a lot of weird.
Yeah, well, all the school districts are a little different, but there's a shining example of one where I would be very surprised to see that problem from a Chatfield geometry student. And I don't know why. It's just one of the fields of geometry that Chatfield doesn't cover. I'm sure there's probably some that they do, and the Rock Canyon does not. But
we do have a problem. It's a right triangle with one side 32, one side 29, and the angle, the smallest angle, is not known, and we have to find it.
it is a right triangle?
Yeah.
Okay. Where's the smallest angle? Is it angle 1 or angle 2?
It could be the one, I think it's the one that's...
Has to be the one opposite the smallest side. So
okay.
Angle
yeah, so
2, angle 2 is the smallest of angle 1 and 2. Now, how do you get it? What is angle 2 equal to? What trig function relates that number and that number and angle 2?
Not sure.
Tangent. So I could say the tangent of angle 2 is equal to the opposite side over the adjacent side. 29 over 32.
I'm sorry, one sec. My parents are being really loud.
Okay.
One sec. Dad, could you lower the piano? Dad, the piano's distracting me. Sorry about that.
That's all right. Now, once you decide that it's the tangent trig function, now to solve for angle 2, you need to take the inverse tangent of that ratio.
Is that the one on the negative one?
The one that's got the negative 1 up top. Yeah, that's the inverse tangent. It's going to be close to 45 degrees. I'm going to guess that it's about 42 degrees without putting it in my calculator. Do you have a calculator? Can you do that calculation?
Yeah.
Go ahead and do it. Let's see what you get.
I haven't done this in a while.
Well, all the better that you do it, because you're probably going to have to do it for your test, aren't you?
Probably. Today I had my Spanish final and my English final, and it was pretty difficult.
Yeah, imagine. It's hard enough to just prepare for
I got
that.
42.1.
How much? 42?
Yeah.
Yeah, that sounds right. Because you know the other one's complementary, so this one has to be 47.9. This one's 42.1. They're going to be relatively close because 29 is relatively close to 32. That's almost an isosceles right triangle. But you definitely are going to need a trig function. And there's no way to solve this without trig, if that's all the information they gave you. In other words, if they gave you, you have a right triangle and these are the two short sides, figure out the shortest angle, that's the only way to do it.
The picture, they made it look a lot, really, different. I don't know. They made the shortest side look a lot shorter.
Yeah, they won't always draw it to scale, but you don't need it drawn to scale. I didn't really, I drew it closer to scale. What you need to know is that angle's trig function regarding the two values that you have is tangent. It's not sine, it's not cosine, it's tangent. Because it's opposite over adjacent. In other words, you definitely need to remember your trig SOHCAHTOA.
Couldn't it be, sorry. Wait, when you're solving for the angles, it's different though.
Right. When you solve for an angle, you're always taking inverse trig functions. Okay? Well, notice what I did. I started out with a trig function. Then I took the inverse trig function of both sides to get angle 2. And the inverse trig function of the trig function is just the angle. In other words, this is kind of by definition. If the tangent of angle 2 is equal to 29 divided by 32, then by definition, angle 2 is equal to the inverse tangent of that ratio. Now, let's say they gave you, instead of the two short sides, let's say they gave you one short side and the hypotenuse, and they told you that that was the case. Okay. Now, we almost have to figure this out because we don't really know whether this side is shorter than 29 or longer. I can certainly figure out that angle. How would I figure out theta if they gave us this model?
Wouldn't you do the inverse function?
Which one?
Wouldn't it be opposite hypotenuse?
Yeah. In other words, the known, we know the opposite, we know the hypotenuse. Well, that's sine. So the sine of theta would be 29 over 40, which means theta is the inverse sine of 29 over 40. Now, I don't have any assurances that that's the smallest angle yet. I'll certainly find out when I solve it. If that angle is less than 45 degrees, it's the smallest. If it's greater than 45, then this one up here is the smallest. But what's important is that you know which trig function to use to solve for angles, because they're always going to give you the two key numbers. It's their position that determines which trig function you use to solve for that angle. Let's take a right triangle that you're very familiar with, 3, 4, 5. Okay? What you're probably not familiar with is what is this angle theta? Nobody ever talks about what that angle is. Well, what is it? How would I get it?
This is a right triangle. Wouldn't it be it could be 30, 60, 90?
It's not. I know what it is. It's not a 30, 60, 90. How would I get it, though?
You have to use the inverse thing.
I could use any of the three trig functions because I have all three sides. So pick one.
So sine.
Sine? Inverse sine of what?
It would be 3/5.
Yeah, 3 over 5. That'll give you that angle. That angle is also the inverse cosine of 4 over 5. It's also the inverse tangent of 3 over 4. In other words, depending on which side you know, that depends on which function you use. It's probably not very often they're going to give you all three sides like I just did. They're going to leave one of them off. In other words, they'll tell you these are the two short sides, figure out the short angle. Well, in that case, you got to use this inverse tangent.
Can we do another problem now? I was just looking at it.
Yep. Go ahead.
This one says find the height of the parallelogram.
Okay.
And it's 6 on the slant height on the slant and 7.8 on the base, and then it has like the dotted lines to make it look like a square, like between, like not there, but like to the right side between the top part, like where there's nothing down to where the base would be if it kept going.
Oh, like over here.
And then there's a height from the obtuse angles.
Okay.
each other. That's supposed to be the height you're finding.
Right. In other words, this is height. So,
no, that's not height.
okay, I'm confused. What?
The height, it's like from the obtuse angle on the left down to like just below the midpoint is a 90-degree intersection.
The obtuse angle on the left, which is that angle there.
And it intersects into the right side of the triangle at a 90-degree angle.
Right side of the parallelogram?
Yeah, and that's the height you're supposed to be finding.
So that's what we're trying to calculate?
Yeah.
And that's a right angle there?
Yeah.
Okay. And they give you any other measurements besides the 6 and the 7.8?
Yeah.
So that's 7.8 up there.
Oh yeah, 6.5 is the slant height.
6.5?
Is the slant height. 6 is just the height of the dotted line.
Oh, the vertical height. Okay. Okay, so that's 6 there. I got all my dimensions right?
Yeah.
Well, let's see. How are we going to do this?
Yeah, I'm not sure. That's what I'm asking.
Yeah, I know. No, I'm not positive either. That's why I made the statement.
I honestly don't remember doing this.
Well, let's see. We know it's a parallelogram. So we know
Yeah, but you don't know how to do it.
well, I don't know how to do it right off the bat. It's a problem I'm going to have to think about for a while. It probably has to do with angles. But in order for us to calculate h, we're either going to need this side or we're going to need one of these angles. If we knew one of these angles, then we could use a trig function to calculate h. In other words, if we knew that that was like 52 degrees, we know how to solve it. The question is I don't know how we solve for that angle.
Yeah, I'm not sure.
They haven't given us any angles. However, we have this right angle here, and we have this hypotenuse, and we have that measurement. So we can solve for x easily. Huh.
Are you still confused a little bit?
Yeah, so let's go on. Let's not waste time in me trying to figure it out.
Okay, let's see.
I mean, geometry comes in all kinds of flavors in terms of degrees of difficulty. And so it's not the first time I've run into a geometry problem I couldn't do in live time. And it won't be the last. But yeah, it's not in your best interest to have me spend 10 minutes trying to figure it out.
Yeah. Let's see. I'm trying to find one.
Okay.
Are you able to do a little bit longer than an hour or no?
I'm not. I have another session is the moment you're done.
Okay, let's do...
You sure you don't want to take a picture of these? You can take a picture of these and send them to me. I'll have them in 30 seconds.
Okay. I'm just trying to find an actual one. Because not all of them. I know there's ones that I need to see. But I'm just trying to find the ones that are okay, I have one.
Okay. One, can you describe it, or do you need to take a picture of it?
I'll send it to you on text.
Okay. Let me give you my email. Don't send it to my phone, because then I'll have to figure out how to send it from my phone to my computer. There's my email. Send it to my email. And if you're taking it with an iPhone, make sure you send it as a large image, not a small image. Did you send it yet?
Oh, Mommy. I just have to David.
Right here. That's David Cowan, 1949 at gmail.com. Okay, meaning you sent it?
Yeah, I just sent it.
Haven't gotten it yet. Sometimes it can take a minute, but sometimes people will misspell my name and it never gets here, or something like that. You put the 1949 after my name and you spell it C-O-W-A-N?
Try it again. Just look at it again. I sent it to you again.
Okay. There it is. Thank you. Now I can snap that right. I can open it up. Okay. This is by far the better way to go. Which problem do you want to do?
The first one.
Number 61. Okay, let me zoom in a little bit on it. All right. For all of these circle problems, the way to start each one of them is the general formula, starting with the angle they give you. In other words, this is two secant lines that are intersecting outside the circle. So that angle is equal to what?
Would it be 1/2 59 plus the variable?
No, it's the difference of the arcs. So it's 1/2 of the question mark minus 59. See that? In other words, the question mark being arc TU. This angle is the difference, 1/2 of the difference of the two arcs that are intercepted. Well, one arc is TU, the other arc is SQ.
Okay.
They want to solve for TU. So let's put TU right there. And now all we have to do is solve that equation.
Yeah.
What's the first step?
You multiply it by 2.
Correct. So now I get 60 equals arc TU minus 59. Add 59 to both sides. That's the measurement of arc TU. But the key is knowing those general formulas. Now, one help I can help you with is that when you're intersecting outside of the circle, it's always the difference. When you're intersecting inside of a circle, it's the sum. In other words, 62, it's still 1/2. But if I want to know what arc, in other words, 93, start with the inside angle. 93 is going to be 1/2 of the sum of 77 plus arc ML. Now you just have to solve that for ML and you have your answer.
So if it's inside the circle, it's plus.
In general, yes.
Unless it's some funky number.
Well, all of these circle problems, you're either solving for angles or measurements of arcs, or you're solving for segment lengths. For example, 63, we're not solving for any angles. Notice that 63 looks just like 62. The only difference is 62 has nothing but angles and degrees on it. 63 has nothing but segment measurements. So what's the general formula for 63? What can I say when I have two intersecting arcs inside the circle, but there's still a formula that applies here? Excuse me, intersecting chords, not arcs, chords.
I'm not sure of the formula.
It's this segment times that segment is equal to this segment times that segment. So I end up with 9 times x equals 6 times 12. What?
Aren't they different sizes?
No, I don't know what you mean.
Like, are the whole lines different sizes, or are they the same size?
Doesn't matter. In other words, whenever I have a circle, and I can put two intersecting chords like that, okay? And the same thing. If that is A, and that is B, and that is C, and that is D, then I have A times B is always equal to C times D. If I have two chords intersecting inside the circle, that's always true.
So in 63, that would mean 12 times 6 equals 9 times x.
Exactly. Okay? Now, that's a little different than 64. The difference being we're intersecting outside. In other words, 64, in fact, let's do 65 first. Because 64 makes more sense if you've done 65 first. Whenever I have two secant lines, those are secant lines, okay? And they're saying this side is 5, this side is 4, this side is 6, and this is x. Well, it's similar to intersecting chords, but not really. When you have intersection outside the circle, it's this segment times the entire thing. So it's 5 times 5 plus x equals 4 times 4 plus 6. You see the difference? So it's not 4 times 6 equals 5 times x. It's 5 times the length of that secant line equals 4 times the length of this secant line. So now you still end up with an equation with only one variable, and you have to solve that to do number 65.
Okay. What I think for the final would, if you were me right now, would you like, he's letting us use a note card on the final.
Put all these general formulas down. Problem is with geometry, there's so many.
Like,
yeah, here's what you want to do. Here's what you want to do on your note card. Draw a picture. On your note card, put your two intersecting chords, label it A, B, C, D, then your note card should say A times B equals C times D. Next note, I got two intersecting secants. You need a picture with each of these. Here I've got A, B, C, D. What's the formula that applies on the second note?
Making this good note card will just like save me.
Yes, well, it better be big though, because if you're going to put these pictures on there, you're going to need some room.
Yeah, I'm going to try and make it like as big as I can.
So what's the equation that applies on the second circle on the right, on the bottom? What is it?
Wouldn't it be 63's equation?
No, it's not. That's why it's a different note. 63 is only for intersecting chords that intersect inside the circle. This is intersecting secant lines that intersect outside the circle. So this equation is not A times B equals C times D. Not the same at all. This is A times A plus B, the entire length of the secant line, equals C times the entire length of that secant line, which is C plus D.
So wait, would that mean, but this is for which number again? 65?
This is for all problems, both of these. That will apply to every problem. Yeah, if we're talking about what to put on your note card, that's what I'm talking about doing.
So basically if one's for inside the circle, they intersect in the circle, one's for like...
Boy, it's not that straightforward. You can't quite use that simple of logic. In other words, it's like you can't really say that when I'm intersecting inside the circle, it's not addition. It's multiplication here, but it was addition when it was involving angles. Okay, so there's a lot of different scenarios depending on whether you have intersecting chords, whether you're dealing with segment lengths, whether you're dealing with degrees. So if you can have a note card, this is what I would advise for a note card. Make sure you understand the second one though. Do you see why it's A times A plus B? It's the segment outside of the circle, which is A, times the length of the entire segment, which is A times A plus B. The length of the whole segment is A plus B. The length of this whole segment is C plus D. So it's always the segment outside the circle times the entire length of the secant line equals the other segment outside the circle times the entire length of that secant line. And that's why on 65, so give me the equation, 65 applies to this note right here. So give me the equation that would result in 65.
It would be...
In other words, if you're going to come up with notes like this, you want to make sure you can interpret them and apply them to a problem.
5 times 5 parentheses 5 plus x equals 4 times 4 plus 6.
You got it. That's the way to apply it, okay? Now, notice problem 64 is slightly different. It's not two secant lines, but it's the same formula. In other words, I can say 18 times 18 plus x. Let me write it for you. 18 times 18 plus x equals 30 times, what's the length of that whole line? 30. So 30 squared. So whenever you have a tangent line and a secant line, it's always this formula. But you can always figure this out because this formula is really the same as that. It's the part outside the circle times the entire length of the line. And in this case, the part outside the circle is the same as the entire length of that tangent line.
Okay.
Okay?
If you were me right now and you had the final tomorrow, would instead of like spending time just studying the material, you guys should spend time making a good note card?
Yes. Absolutely. Because you cannot do anything without these general formulas. The general formulas are the key to all geometry. You should basically start out every geometry problem with the general formula. If I give you a triangle and I say, give me the area of that triangle, let's start out by saying the area of a triangle is 1/2 base times height, and now we'll just fill in B and H. So it's the general formulas that are the secret to success. And in fact, I have come to that conclusion with some of my other students, and the last section, or the last tutoring session I have with them, is going to be just going over all of the general formulas.
Okay.
Okay. Which general formula? Let me label these for a moment. That's 1. This is 2. Which of those two formulas applies to problem 66?
1.
Okay, so what's the equation I can write from 66?
8 times, I think, 14. 8 times 8 times 14.
No, just 8 times 14, one time.
Oh yeah, sorry, I was thinking the second one. For some reason equals 7 times x.
Right. In other words, here you're just multiplying this segment times that segment equals this segment times that segment. Intersecting chords are the easiest to do. Much easier than 65 or 64. Because this one you have to do 18 times 18 plus x equals 30 times 30.
Okay. Before you have to go,
How about these problems at the bottom here? The standard equation for a circle. Let's make sure you have that. What's the general equation? Here, draw a tiny little circle. You don't need much of a circle for this, but here's the general equation. And this is what needs to go on your note card. Where H is the x-coordinate of the center, K is the y-coordinate of the center, and R is the radius of the circle. Okay? So what would the equation of that problem you got your thumb over in the picture?
it would be, well, the x would be...
No, the x, you don't fill in anything for x. What you need to figure out is what is h, what is k, and what is r. And then we'll fill in those.
Yeah.
So what's
well,
h?
I'm just saying in general that the h would be -7, but with that it would be +7.
Correct. So that part, okay.
Plus y minus, plus 1 equals 4.5 squared.
Correct. You got it. And as long as you know this general equation, these circle problems are going to be a piece of cake.
Yeah.
Now, this 1b, the b is a little different.
But here, can we do one different problem?
Sure. Sure.
I'm not going to try sending it to you because that'll take too much time.
That's fine. No, that's fine.
It's a 60-90 triangle with the smallest leg being 4√3 over 3.
And what's the problem? Figure out the long leg?
What?
What is the question? What do they want you to figure out?
They want you to find, they want you to find the x and y, which are both other legs. I just did that with the radicals stuff, and square roots.
Okay.
That's answering radicals.
Let me give you the easiest way I know to do this problem. And this is something you want to put on your note card.
Okay.
Put the unit dimensions for a 30-60 and a 45-45. By that I mean these dimensions right here.
Oh yeah, I know those. I know
well,
that
what's the similarity ratio between these two triangles? Because they're similar triangles, so every side has to be proportional.
Isn't it the small leg is 2 times the small leg is the hypotenuse?
Well, that's correct, but in terms of solving for x and y, we can use the fact that these are similar triangles. The very first thing you need to do is figure out the similarity ratio. Take the bigger triangle and divide it by the side that's corresponding of the smaller triangle. So what's the similarity ratio?
Like √3.
No, that right there. Because I'm dividing this by 1. In other words, every side of this triangle is that similarity ratio of the other one. So if I know my similarity ratio, all I have to do is multiply it by there to get x, and if I multiply it by 2, I'll get y. So once you come up with the similarity ratio, the problem really becomes very easy. But in order to come up with the similarity ratio, you need this picture and the dimensions, because without these dimensions, you can't use this technique.
Wouldn't it be, could we just work on the radicals, because...
Well, sure. In other words, okay, here, we'll do it. The similarity ratio times √3 is what? There's the similarity ratio, and I'm multiplying it by √3. That's going to give me x. What is that?
Well, we have to keep it in radical form.
Well, even if you have to keep it in radical form, it's 4.
Wait, really?
Uh-huh. The next one won't be, but this one, square root of 3 times square root of 3 is 3. So I have 4 times 3 divided by 3. This measurement is 4 right there. Now, y, the hypotenuse, is going to be the similarity ratio times this hypotenuse times 2. And that is 8√3 over 3, and that's your answer for y. Okay. So on your note card, I mean, as long as you understand this concept of similarity ratio, well, if you know this triangle, I'd still put that triangle on your note card as well as the 45-45 right triangle, which is 1, 1, square root of 2. As long as you know these two triangles, well then given anything that is similar to either of these, you can figure out the sides as long as you get the similarity ratio. Now let me change this problem slightly, just so make sure you understand what we're doing here. What if I said that's 4? What's the similarity ratio? Big triangle to little triangle.
Big triangle.
Yeah, this big triangle up here to this little triangle. What's the similarity ratio?
2 and √3.
No. You measure the corresponding side. You have to measure that versus the hypotenuse of the other one. So the similarity ratio is 4 over 2.
Oh.
Okay? Which makes this side down here 2√3, And it makes this side over here 2. So make sure you understand exactly how I did that, because you're definitely going to have to do problems like this.
Well, what else should I put on my note card?
Mainly, well, that you can't really put on there. That you have to understand how to do. You have to understand this concept of similarity ratio.
Okay.
Okay, let me give you another one. Hold on. I want to make sure you don't lose this concept. What's the similarity ratio now, big to little?
Wouldn't it be 4?
Divided by? What's the equivalent side?
3.
Root 3, exactly. There's your similarity ratio. Okay? Now, if I want this side over here, I got to multiply it by 1. Well, that makes this side 4 over root 3. If I want this hypotenuse, I got to multiply it by 2, because that's the hypotenuse of the little triangle. So the little triangle would be 8 over root 3. Now, of course, each of these has to be rationalized. You can't give an irrational answer. But you know how to rationalize problems?
That's what I don't know very well.
All right, if I'm I got to go here, so I'll do one of them. If I'm rationalizing this, I'm going to multiply top and bottom by root 3. And that gives me root 3 over 3. So this is the same as this, but the circle on the right is a proper answer. The one on the left they won't like. You'll lose points because you gave an irrational denominator. So you always have to rationalize a final answer. You have to rationalize the denominator.
Okay.
Okay? Sam, I'm sorry, but I got to go.
Okay.
All right. Good luck on your test.
Thanks.
All right. Bye-bye.